And now for a little case study on single-thread performance with SIMD. We're going to talk about a particular implementation, Stream VByte. And the question that I want to start out with is, can you run faster just by trying harder? If you've watched any episodes of The Flash, as in the modern 2014 version, you will have seen, no doubt, a trend, a pattern that basically in every episode, whatever problem it is that Barry is facing, he solves it by running faster, and he just needs some inspirational speech about how we are the Flash, or Cisco tells him the correct sequence of words, and then he can run faster somehow. Can you run faster just by trying harder? All right, making fun of CW shows aside, actually, if we invest some effort into it, can we do some domain-specific tweaks? And the answer is yes, and that's a way of decreasing latency. When we look at parallelizing, we're increasing our throughput, we are improving our bandwidth. It makes it a little bit easier to parallelize and increase bandwidth, but not necessarily any easier to decrease the latency. And when we want to do so, sometimes we're going to do something domain specific. And here, the example that we're going to talk about, Stream VByte, is really all about decreasing the latency. And we're going to see if it works, and also, okay, it does, but how does it work? I mean, sometimes your goal of decreasing latency is just sort of classic computer science type stuff. Remember your data structures and algorithms, and if you do, you will note that if you use a better algorithm for some reason, or can swap something in, you could get some improvement. Quantum Flow found a place where they could cache the last element of a linked list, because of course it's the element that you are most likely to want in the immediate future, and that would reduce time complexity for insertion from order n squared to order n log n. And yeah, that's an improvement. It is better. We like it. Of course you do that. But now we're talking about doing things that are really problem specific. So let's do that. Now, Stream VByte uses parallelism, the idea of vector instructions, so the SIMD kind of instructions that we talked about in the previous section. And all that we are doing when we do this kind of thing is we're trying to make it so that there are sequential improvements, and we're trying to do so by being predictable for the branch predictor. That is, when we are trying to predict a branch, is this branch taken or not taken, that is a possibility of getting it wrong and paying a penalty. And if we are careful to behave in a predictable way, it increases the likelihood that the hardware branch predictor will successfully guess what we are going to do. Any little bit helps. Okay, so the problem that we're trying to solve is abstracted to storing a sequence of small integers. This kind of thing happens in the context of an inverted index, which allows, say, a fast lookup by term, and support Boolean queries, which also combine those terms. If that sounds really abstract and doesn't really make a lot of sense to you, then think of something like this. If a document has an ID, and document IDs in this very simple example are 1, 2, 3, and 4, and that is a document that talks about dogs, cats, and cows, then we would say, okay, using the regular index, we could say, okay, document 1 contains dog, cat, cow. Document 2 is only about cats, so it doesn't mention the other animals. Document 3 has dogs and goats. Document 4 has cow, cat, goat. That's the regular index. And then the inverted index is going the other way, which is, if I'm interested in learning about cows, which documents do I go to? Well, looking in the inverted index, I can see, okay, cows are referenced in document 1, document 4. Those are the ones that I need. And those are the kinds of things that we can use to look up different things by keyword, right? This happens a lot in the academic world as well, that if I am publishing a paper, the paper has certain keywords, and my keywords, rather than being dog and cat and other common animals, they are role-based access control and computer security and what have you, and that's great. But somebody who wants to become educated in the topic of role-based access control, they don't want to crawl through every document and see, is this relevant or not? They want the inverted index. And so in this scenario, our inverted index contains a large number of small integers. So that's okay in this scenario, especially because we are saying our document IDs are 1, 2, 3, and 4. Clearly, in a document system that contains more than a handful of documents, the document IDs are going to be a little bit longer than this. However, we can reduce the amount of storage that we need by storing a delta. So we're saying, okay, instead of documents 1, 3, 4, 7,000, 9,000, and so on, we would say, okay, just the difference in the number. So if the current document is 78,122 and the next document is 40 later, you would store 40 as the next thing, because that tells you just add this to your current index and that gets you where you need to go. That does usually mean that deltas are relatively small, and particularly if the document IDs are sorted, you just go to the next one and the offset is easy to calculate. Going from deltas to original integers takes a time that's logarithmic in the number of integers that we're examining. And so stream VByte is based around this with a combination of a thing that we talked about previously, which is using fewer bytes when we don't need all of the bytes. If the data that we are storing can fit into a smaller amount of memory, we'll store it in a smaller amount of memory. If we need the full 4 bytes, then we'll use the full 4 bytes. So that's just how to make most efficient use of that memory. Use only what you need and nothing extra. So that's the approach. And this is, we expect to benefit because most integers in the scenario we are describing are small, and small in this sense is in comparison to the maximum value that can be stored when we're talking about a 64-bit type. If it's a word size where the processor is 64 bits, so that makes it easier to do this efficiently. So VByte works like this. So if the number that we are talking about is between 0 and 2 to the power of 7, that is to say it's small and it fits in 1 byte, then we have a control bit that represents whether or not there is more data to come. So the first bit here is 0 because that's our control bit, and then the rest is the actual number. Okay, fine. If the quantity is going to fit in 2 bytes, then again, we are reserving our first bit as a control bit, and the rest are used to represent the number. So for the first byte, the control bit is 1, saying there is more to come after this. This is not the last byte of this, and so on and so on. And we can keep going in that scheme. And the control bit, the highest order one, is basically saying 0 if this is the last byte representing this integer, and 1 if it's not. So, all right, we've built in there a little way of signaling whether or not we have reached the end of the particular number that we are interested in. In this sense, it resembles, to at least a small degree, the way that a string is null terminated in C. You don't get in advance necessarily told how long a string is. Instead, you get well, the string ends when we get to a null byte. As you will recall, if you've got significant experience programming in C, sometimes that goes horrifyingly wrong because you forget the null terminator and you end up with a lot more data than you were expecting. Here you get at least a little bit of information in advance that says, look, this is the last one or not the last one. Okay, so this is, well, you might think, not going to work very well, because it seems like dealing with these variable byte integers is actually harder. When we deal with a fixed byte integer, we know exactly what we're going to do, take the next thing and do it and go. On the other hand, there are potential performance improvements. We are using fewer bits, so we could fit more information into our RAM and limited cache, and can potentially get higher throughput as a result of that. Right? Fewer cache misses, better performance. So it sounds like there's something here. Storing and reading all these extra zeros is not an effective use of resources, but unfortunately a naive algorithm to decode this gives a lot of branch mispredictions because it really doesn't know in advance whether any particular integer is going to be of 1 byte in length or 2 or 4, so it's easy for it to get it wrong. So we need to improve on this to really take advantage of the single instruction, multiple data kind of nature of it. And that takes us to stream VByte, which is a variant that is intended to use SIMD instructions. And as you will know, science is incremental. Stream VByte builds on some earlier work, masked VByte, varint GB, varint G8IU, that sort of thing. But the innovation that in stream VByte makes the difference is the idea of storing the control and data streams separately. We just went over, when talking about how VByte works, the idea that we're going to store at the beginning, use the highest order bit to make a claim about whether or not there's going to be another byte of this same integer. But actually, we're going to say that's not ideal, and it would be better if we split it up. One of the things that makes this worthwhile was something that we mentioned very briefly when we talked about caching and cache coherence and the idea of cache miss rates, is that there are separate level 1 data and instruction caches. That makes a difference that is kind of meaningful, because if we can keep the instructions in the cache as we swap out data, that's better than having to do both. Right? We want instructions that are going to be repeated and going to be reused to stay there in memory, and those that are not can get flushed. And data we're more likely to need once and then be done with it, as opposed to need it again, because if we are doing a large calculation, we're doing the same operation on different data elements. The data elements change, but the instructions stay the same. So we have a control stream, and the control stream uses 2 bits per integer to represent the size of that integer. So while we're reading the control stream, we always read it 2 bits at a time, or we look at 2 bits at a time anyway if we're analyzing it as a human. And we say, okay, if we see 0, 0, that means that the next integer is 1 byte. If we see 0, 1, it's 2. If it's 1, 0, we see it's going to be 3 bytes. If it's 1, 1, then the next integer is 4 bytes. And that way the control stream is always fixed in length, right? For whatever we are looking at, we always look at the upcoming 2 bytes, sorry, 2 bits, to determine what the length of a given integer is going to be. And so each decode iteration reads 1 byte of the control stream and 16 bytes from memory. And it uses a lookup table over all the possible values of the control stream to decide how many bytes it needs out of the 16 bytes it has read. If the control instruction said everything is 4 bytes, then of course reading the 16 bytes and processing the 16 bytes happens as one step. If the control stream is at the opposite end of the spectrum, where we have everything is going to be 1 byte types, then we're actually really only going to process some of the data and not everything. We'll process the 4 bytes of the 16 bytes that we have read, and that's okay. We'll just keep track of the data that we needed. And then there are SIMD instructions to shuffle the bits each into their own integer. So we've read 16 bytes. We're going to split it up according to what our control stream says is correct, and then move those to their own little registers, and then perform the operations on those in an efficient manner, and we're good. That gets the computation done very quickly. Maybe, again, in the scenario where the control stream was not all ones, we read some data that we didn't end up moving into its own integers and shuffling, and that's okay. We can just do it again, and we will move those bytes on the next round. Okay, so if the control stream is in binary 10001100, that tells us that the integers that are upcoming are of size 3, then 1, then 4, then 1. So of the 16 bytes read, this iteration uses 9 bytes, so it advances the data pointer by 9. Then the shuffle instruction in SIMD puts the decoded integers from the data stream at known positions in the 128-bit SIMD register, and that also does whatever padding is necessary. So pad the first 3-byte integer with 1 byte, that's all zeros, and then the next 1-byte integer is padded with 3 bytes. The one that's already 4 bytes in length doesn't need any adjustment, and then the last 1-byte integer is again padded with 3 empty bytes so that it fills up the space accordingly. Okay, and 4 32-bit integers fit, of course, perfectly into the 128-bit SIMD register, so we're doing well in that regard. So if our data input is this, well, some hex F8, 23, E1, 27, and so on, and the 128-bit output is as is shown on the slide, where the slashes denote separation between outputs, we are pretty clear and obvious on where the separations happen, because our control stream told us where to put the dividing lines and how much padding to add. In the control stream, we said, okay, the first one is 3 bytes, so we add 1 byte of padding. The 00 at the beginning of the 128-bit output is that extra 1 byte of padding that we have added for that first integer. Then if we follow the slash, then there's 3 pairs of zeros, and again, that's 3 bytes of padding that we are adding to that normally 1-byte integer. And so on, and this continues so that our output is correct and is filling up our 128-bit register exactly the way we would expect. To make it efficient, of course, the control stream, as we said earlier, uses a lookup table to decide what is going to happen, how many bytes to advance by, and same thing with our moving of the data. The shuffle mask is what we call it, and that's saying, okay, move these bytes to there, and based on the control stream, we know, okay, the first 2 bytes go in this position, and then the next bytes go in that position, and so on, and it is just read from an array, so all that stuff is easily pre-computed, so we can save on some CPU cycles. And the core of the implementation does something like this, that we get a value from the length table based on the control stream, and then we increment our control byte at the end, which will, of course, be used to figure out what goes on next. In the meantime, we load our data into a 128-bit register. That's why there's a double underscore M128I. It is one of those implementation-specific types. This is a C++ implementation, but you can do the same thing in SIMDs. And then we load the shuffle mask by looking in the shuffle table, again, based on the control bytes, or control byte singular, that we already have. And then we get our data out of that by using the multimedia extension shuffle, by combining our data and shuffle, increase our data bytes by the amount that we have successfully processed now, and then increment the control byte to go to the next one. Okay, that's great, but does it work? The paper discussing this says that yes, actually, stream VByte performs better than previous techniques on a realistic input. And here are some ideas as to why we think this is the case. For one thing, control bytes are sequential. The processor can always prefetch whatever the next control byte is. There's no jumps, there's no loops, there's no branching, there's no conditionals, nothing like that. The next is always predictable. That means that the CPU never gets it wrong. Number two, data bytes are sequential, and they can be loaded at high throughput. If they're packed very tightly, then when we have a cache miss and we need to load in the next page of those integers, we've got more of them than we would if there was a lot of wasted space. And so if most of your integers are small, most of them will be 1 or 2 bytes instead of using 4 bytes for every single integer, and that is potentially a significant savings. The shuffle routine exploits the instruction set. It significantly moves your data around, spreads things out and reassigns them here and packs them correctly in the 128-bit into the 128-bit register. But you don't have to write that. It takes one cycle because the hardware people conveniently implemented that, and whatever dark magic or difficult calculation is necessary to get it from A to B to C, you don't care. Don't have to. It's implemented in hardware, and it is done in one cycle. So, perfect. That's exactly what we want. And the other thing is that control flow is regular. We are executing only the tight loop, which retrieves and decodes control and data, and there aren't conditional jumps. Right? Although the behavior of the shuffle is a little bit different, depending on what your control stream says. You are always going to this address and looking up with a certain offset. It is easily figured out where we're going. So we don't have to wait for a particular thing to be evaluated to know what our data is going to be. Although you could say, well, control bytes could vary or what have you. I mean, this is just an offset. And so when we're doing a read, like the first one here, uint 8 type C, is assigned length table at control. I mean, it's a read, so we're calculating the address as the base address of length table plus the offset, where the offset is the value of control. So that's just an addition. There's no conditional there. Even though you might think about going to a particular array index as being like, well, if the index is this, then go here, or else if, that isn't what happens. It's just an offset calculation. And I'm sure we've talked about that if you took a course with me in C, where we talked about the idea of that, like the square brackets indexing operator kind of thing is really just a mathematical shortcut, and it's why in C you can do a pointer length table plus 28, and that's perfectly reasonable because it's what the compiler does in the first place. And so in that kind of thing, we are not doing any conditional jumps. We're not jumping around anywhere. We're not branching anywhere. There's no decision to be taken. We're just doing an addition. And the fact that it might be length table plus 0 or length table plus 12 doesn't matter very much in terms of prediction. It's just a different operand. So that makes the control flow very regular, and we execute just the loop without any worries. This has been a good way of demonstrating actually that SIMD does what it is supposed to do, and proves that in a practical real-world scenario you could actually make good use of it, and it could improve the performance of your program. There's another thing that's linked in the notes that we're not planning to cover, but you could read more about it if you wished, and it is a Medium post about learning SIMD with Rust, about finding planets, and it is again just another example of using Rust with SIMD to effectively, calculate where planets of a solar system are at any given time. And okay, there is a range in which this computation is valid, so it has to be 2000 of the current era plus or minus about 4,000 years, depending on the planet. And there's a relatively predictable way of figuring out where the planets are going to be. Of course, you could just use SkyMap or something like that. That source also gives you a reminder, by the way, that using SIMD in Rust is unsafe code, so you do have to be very careful about this, and you should audit your unsafe blocks appropriately to make sure that nothing really weird happens, or that you are certain that there aren't any mistakes in there.